Welcome back to another explainer. So if you're a focused learner trying to cut through all the noise and get straight to the facts, well, you're in exactly the right place. Today, we're kind of putting on our detective hats to uncover visual bias and really discover the proportional truth in data visualization. We're going to look closely at how the very tools we use to track progress can sometimes completely distort the reality of that progress. So get comfortable and let's get started. Now, have you ever wondered when a standard line graph might actually be lying to you? I know it sounds a little dramatic, right? But honestly, in clinical analysis, spotting this kind of visual bias is absolutely crucial. In fact, exam creators literally love to test this exact scenario. They know that if you just glance at a standard graph without understanding its underlying architecture, you can be so easily misled. Today, we're going to learn how to spot exactly when that seemingly straightforward graphical display is just hiding the truth. All right, let's look at the exact scenario we're dealing with. We're specifically zeroing in on graphic displays under domain C, where a behavior suddenly skyrockets. Think about it. Imagine a learner whose progress just takes off. You plot it on a graph and it looks awesome. But beware, you might be stepping right into an architectural trap. Sometimes a chart looks like it's telling the whole triumphant story of a skyrocketing behavior, but because of how it's actually built, it completely fails to show the true rate of learning. Okay, let's dive into this. The standard equal interval line graph. You know, the one you've probably seen 1,000 times. The big trap here lies in tracking absolute changes. See, in the standard linear format, equal vertical distances represent equal absolute amounts of behavior change. That right there, that is its core architectural trap. It only tracks absolute additions. It honestly doesn't care at all about where the behavior started. It only cares about the raw number of units added. And relying only on absolute additions can completely blind you to the reality of a learner's progress. Let's actually walk through this specific architectural trap by comparing two distinct learners. Take the first scenario. A learner makes a jump from 2 to 4 words per minute. That's an absolute addition of 2 units, right? Now, compare that to a second learner who jumps from 50 to 52 words per minute. Again, an absolute addition of exactly 2 units. On an equal interval line graph, both of these jumps appear as completely identical, 2-unit vertical jumps. Visually, the chart tells you that the exact same amount of learning just occurred in both scenarios. But is that really true? Well, think of it this way. Going from 2 to 4 is a massive doubling of performance. It's like a toddler suddenly speaking in full sentences. Their entire capacity to communicate literally just doubled. But going from 50 to 52? That's just a drop in the bucket. An auctioneer wouldn't even notice the difference. Yet, the linear graph treats a monumental doubling of performance exactly the same as a tiny, barely perceptible drop in the bucket. So the crucial point we really need to look at here is proportions. That jump from 2 to 4 represents a massive 100% increase in performance. It's a huge proportional transformation for that learner. But because a standard linear graph only tracks absolute additions, just a simple plus 2 units, that incredible 100% relative reality is completely hidden. The line graph visually flattens that monumental achievement right down into a tiny, unremarkable tick mark. And if you're analyzing clinical data, missing a 100% increase because of a faulty visual display, that's a massive analytical error. Enter the hero of our story, the Semilogarithmic standard celeration chart, or the SCC for short. Now, unlike our linear graph, this chart completely solves the architectural trap. Why? Because its vertical axis tracks ratios, not raw numbers. This means that doublings will always look identical on the grid. Going from 1 to 2, 2 to 4, or 50 to 100 will all take up the exact same amount of vertical space. It charts true relative growth, completely abandoning that misleading focus on absolute additions. And this brilliantly illustrates how the SCC actually processes these inputs differently. For that first scenario, it honors that massive 100% doubling, giving the jump from 2 to 4 a huge amount of visual space. Meanwhile, for our second learner, that 2-word addition between 50 and 52, it shrinks right down to the tiny drop in the bucket it truly is. The chart finally matches the practical clinical reality of what the learner is actually experiencing. When you see straight celeration lines slicing sharply upward through a semilogarithmic grid, you are looking at true clinical precision. You aren't just seeing some distorted curve that flattens out low frequencies. No, you're looking at straight, precise indicators of how fast a behavior is multiplying or dividing over time. They are tracking the relative ratio of learning and behavioral fluency. It is just the highly precise proportional way to view human learning. So, how is this actually built into your strategy? Especially if you're prepping for an exam or just refining your clinical toolkit, here is exactly when you must abandon linear charts. If your focus is precision teaching, you select the Semilogarithmic standard Celeration chart. If the focus is on behavioral fluency, you select the SCC. And if you're tasked with evaluating the proportional speed of learning over time, yep, the SCC is absolutely your ultimate tool. Now, why does all this technical distinction actually matter so much? Well, you have to protect your data from the visual flattening of low frequencies. Think about it. If a learner is just starting out, operating at a low frequency of maybe 1 or 2 behaviors per minute, a standard linear graph is just going to visually flatten out all their hard-won progress. The SCC protects your data, ensuring that your clinical analysis remains flawlessly accurate by honoring every single proportional leap that a learner makes. So I'll leave you with this provocative question to chew on. Is your chosen chart actually illuminating the proportional truth, or is it hiding the true speed of learning? Your job now is to log into your dashboard, master your charting matrix, and make sure you never fall for visual bias again. The proportional truth is out there, as long as you're using the right grid to see it. Keep questioning the data, and thanks for exploring with me today.